Thanks for the introduction, Frank. Yeah, I'm really happy to be here and to talk to you today about provisioning techniques. So we've seen a lot of, let's say, modeling techniques and abilities to deploy different kinds of systems in the cloud. And okay, how it works. So as a simple motivation scenario for my talk, I will introduce a very simple application stack that is basically WordPress, a software system that you may know. It's an open source software based on PHP that you can run your blog online, basically. The application topology looks like this. So you have the application itself, which is connected to a database. Then you need some middleware components like a PHP runtime environment to host the application and a MySQL database server for the database. And of course, you need some infrastructure components. For example, two VMs, one VM is hosting the application, another VM is hosting the database. You could combine them, you could also deploy it using Bluemix in a pass manner. Of course, there are different alternatives, right? But conceptually, there are a bunch of operations that you need to invoke or that you need to call when you want to deploy such a stack. You need to care, for example, about that the underlying machines are created properly. For example, you use a cloud infrastructure provider such as Amazon Web Services to provision EC2 machines as a basis as a foundation for your topology. Then you might have some scripts, for example, chef cookbooks that I will introduce in a few minutes, that basically implement these operations, because on an abstract level, these are operations that are defined, that have to be defined somewhere, but they still need to be implemented. Like in object-oriented programming, you have some abstract classes, some method definitions, but at some point in time you need to implement them. And of course, you can now use different kinds of technologies. For example, you can use chef cookbooks that are shared by open source communities to reuse these artifacts to deploy middleware components that are often used, because there are many application stacks that, for example, include a MySQL database server or a PHP runtime. So it makes sense to reuse those artifacts that are already publicly available and maintained by the open source community. But for example, if it gets more specialized, for example, on the level of your application and the database that you're using, you might have some custom shell scripts to deploy some customized application components on top of the middleware. And then you also need to take care that this connection between the different application components is set up properly. So you might have some connect operation that is, for example, implemented by a workflow. And then last but not least, you also need some mechanism to orchestrate all these things, basically. So this is what we have seen in the talk before, this imperative versus declarative processing. So you could have an overarching provisioning plan, or just a topology model like Tosca that you process declaratively by a Tosca container, by a Tosca engine, right? So why provisioning automation at all? So from my point of view, one major point is that typically in traditional environments you have a strict split between developers, architects, and on the other side the operations people, the administrators that actually take care that your software is running in production properly, right? And in order to enable fast and frequent releases, these two groups of people need to work much closer together. So we require, in order to enable fast and frequent releases, which customers typically expect, especially for systems of engagement, what we have seen in the morning, we need efficient and tight collaboration between these two groups, and therefore we need a holistic automation approach. And this is one of the major ideas of DevOps. So bringing together these two groups, also on a conceptual level, and implement some very holistic automation approaches in order to enable this. The only problem is that today you have a plethora of provisioning automation possibilities. So if you have a look, there are Chef, Puppet, for example, to do configuration management. You have a set of libraries that you can use to automate provisioning tasks, to speak to different cloud provider APIs and stuff like that. You have different modeling techniques, for example, Amazon CloudFormation, Tosca, Hot, and stuff like that. So there's a huge variety of technologies model-driven approaches and other approaches out there, right? And even you have to think about combining them, because they are typically not only used in an isolated manner. For example, as we have seen before, in Tosca you typically orchestrate on the level of implementation artifacts different kinds of scripts. So one implementation artifact could be implemented by a chef cookbook, for example, published by the open source community. Another artifact could be implemented by a shell script and stuff like that. So this is just that you get an impression that you may have heard of some things. For example, we have seen Bluemix in the morning that is based on Cloud Foundry, which is an open source framework to build your own path. You have some configuration management tools. Docker is very hyped at the moment, a kind of container virtualization approach that I'll introduce later on in more detail. And there's a bunch of other stuff. For example, standards like Tosca, OVF. For example, OVF you can use to package virtual machine images and stuff like that. And not only these approaches are available, but you also have some very active communities behind some of the tools. For example, the Docker community is currently very active in creating very fine-grained application and middleware containers to reuse certain components in different application stacks. You don't package whole virtual machines, you just package in the container what you actually need in your stack. I will introduce this later in more detail. On the other hand, you have, for example, some script-centric approaches like chef cookbooks providing some kind of declarative language to exactly define what you need to do. This is also sometimes referred to as infrastructure as code, so you codify all your operations knowledge in such scripts. And there's also a very active community out there that publicly shares a lot of artifacts to be used, for example, to operate very common middleware components like MySQL database server and Apache web server and so on. So the problem is we have a lot of stuff out there, and it's really hard to decide, right? And even it's somehow hard to find out how these things fit together. So as I said before, we don't have these isolated solutions. We also have to find out how to combine, for example, Chef with Docker and how it fits with Tosca and so on. So what we need in the first place, we need some kind of systematic classification, or we need some way to go there to classify those provisioning automation approaches somehow. And this is basically the enabler for some kind of decision support that leads us to informed decisions. Because at the moment, what we see very often in the open source communities, a lot of decisions are based on gut feeling, right? And this is not what we typically want. We want some indicators how to decide, for example, which solution to be preferred for a certain scenario, for a certain application stack. Right? And there are, I will not present the overall solution. I will just present a few dimensions you could consider here. For example, one dimension would be the level of dependencies, how I named it. So you have solutions, for example, like Amazon Web Services or Heroku, which is very similar to Bluemix conceptually. They are provider dependent. That means if you are using directly those services, you are basically locked in to, for example, Heroku. If you use their platform, if you stick to their services and you build your application on this platform, it's very hard afterwards to move into another cloud. So you're bound to the provider. Then, on the other hand, you have some tooling dependent approaches. That means you have dependencies on some tools, for example, on Cloud Foundry, if you stick to Bluemix, but you could, for example, go to another vendor that also uses the same tool or framework in the background. That means you can more easily move your application to another provider. And last but not least, you have the standards-based approaches. If you stick to Tosca, you can deploy your application model to any kind of engine that basically implements a Tosca standard. For example, you can go with OpenStack Heat, you can go with other implementations, for example, provided by companies as IBM. So these are the levels of dependencies you have to consider when you decide for a certain solution, right? Because afterwards, it might be tricky to, for example, if you are here on the level of provider-dependent solutions, then it's very tricky to move to another provider. Another dimension could be the level of virtualization. So when we go, for example, at the low level, you see typically hardware virtualization. You have hypervisors that offer you different kinds of hardware virtualization. These are basically virtual machines, right? So you have abstracted away the physical servers, the physical storage. You just go to the Amazon API and say, you know, I need a virtual server of this and this size and so on. On the other hand, there's another category emerging which is not new. It's container virtualization, and this is on the level of the operating system. The difference between virtualization, hardware virtualization and operating system virtualization is basically that you don't package a complete operating system for each VM. So you can, for example, run multiple containers on a single operating system. That means inside one virtual machine you run several containers with very different applications, for example. So you don't only have this level of hardware virtualization. And then, last but not least, we have the level of middleware virtualization, which is basically the layer of platform as a service. That means basically you use middleware services directly without provisioning them. You go, for example, with Bluemix, with any Cloud Foundry instance that is out there, and you just say, okay, I need this MongoDB service, you get your endpoints, and then you just use it. You don't care how it is deployed in the background, how it scales, and so on. This is part of the provider's work, right? And this is why it's called middleware virtualization. And yet another dimension could be code versus image. So, for example, when you stick to this approach of virtual machines, you are typically dealing with images. So you have some pre-packaged virtual machine images. These could be, of course, in OVF, so you have it in a more standardized manner, and you could throw it to different kinds of hypervisors. But in the end, you have some image that packages all the application and middleware components that you need. On the other hand, you could also go for some more code-centric approaches. For example, Chef and Puppet provide you domain-specific languages to codify all the operation knowledge in a style that is called infrastructure as code. That means basically you define all the resources, all the commands and stuff you need to execute in order to provision and to deploy all your application and middleware components in your application stack. This is also something you might consider. So, for example, the code you can easily rerun. For example, if the images get out of date, for example, if you have an image that packages a whole operating system, it might be cumbersome to update it later on, because you don't exactly know how it was built. Maybe there are some configurations in it, and if it's not well documented, it's hard to reproduce. If you use the code-driven approach, you can easily just rerun the scripts and basically build a new image based on that. So there are, of course, further dimensions you could consider. For example, infrastructure-centric versus application-centric approaches. We have seen this already. For instance, the Bluemix approach, or in general the platform as a service approach, is much more application-centric, because you actually focus on the application requirements and how to resolve them based on the middleware services that are offered by a certain provider or by a certain framework, for example. On the other hand, for example, creating a heat template is much more focused on the infrastructure levels. That means you think about how to orchestrate virtual servers, how to orchestrate storage, how to orchestrate networking capabilities and stuff like that. So you are much more on the level of thinking, what do I need in terms of infrastructure? What scripts do I need to run on these infrastructure entities and so on? And on the other hand, we have seen it already in the talk before, declarative versus imperative. For example, Tosca plans, which are basically workflows, versus, for example, Cloud Formation template, that is a domain-specific language defined by Amazon, which is very similar to HOT. And we will see later on in this talk how it works. So we will see 3 deep dives during this presentation. I will start with Chef as a major representative of this script-based configuration management approach. Then we will have a look at Docker to see how to implement container virtualization on the level of the operating system. We will see how CloudFormation works. This is basically an infrastructure topology modeling language provided by Amazon. And we will also see how to combine, for example, Chef and Docker in order to build containers, and how to use the CloudFormation in order to orchestrate different kinds of technologies. Alright, so let's get started with Chef. So Chef in a nutshell is basically you define the configuration of resources based on recipes, and Chef provides you a domain-specific language which is based on Ruby, technically. You can do declarative statements, but you can also do imperative statements. For example, you can just define a statement that says you have to ensure that a MySQL server is installed on this machine, but in some cases it might be easier, or you might prefer imperative statements where you just give the system command. Of course, this is not so portable, because if you run this command on a Red Hat machine, it might not work. So you always have to consider this difference. Declarative processing provides you some abstraction, but it's not available for all the actions that you need to perform in order to deploy your application stack. Technically, these recipes are bundled in cookbooks, so you have a cookbook that serves a number of recipes. For example, these could be the lifecycle operations. You could think of, for example, a MySQL cookbook that has an install recipe in order to give you a means to install the client, the server, and so on, and maybe some plugins, modules that you need. The Chef itself, the server and the client, is open source software, so you can just download it and use it. However, the company behind it, they also provide an offering which is called Hosted Chef. So you can also use the management capabilities that the Chef server provides as a service. So you don't have to install your own Chef server. You can also just go there, pay for using the Chef offerings that they have. Technically, you could have different entities in the cloud. So you could have virtual machines, you could have some physical servers, or some other cloud instances, for example, containers that are running on top of virtual machines. These are also instances that are running in the cloud. And now the Chef server is basically the central component that has all the knowledge. So it stores in the node objects the information which cookbooks have to run on which machines or on which instances in the cloud. This is the basic idea. So the Chef server is the central entity, and then you have several nodes of different kinds. And these nodes could be even distributed among different cloud providers. Then you have the administrator's workstation. That the administrator basically has a tool which is called Knife in order to interact with the Chef server. So technically, the Chef server implements a RESTful API. You could also use this API programmatically to integrate Chef with your favorite orchestration and management tooling. But they also provide some workstation client here, and you usually have a repository in order to store all this infrastructure code that you write and to version it and so on. That means you can basically pull out the code, use Knife to say, okay, I have to run this cookbook or this recipe on a certain machine, and then the Chef server takes care that it's executed on the machines that are supposed to. What Chef technically implements is the concept of convergent provisioning automation. This is not something that is specific to Chef. There are other tools out there, for example Puppet, that implement the same mechanism, and I will shortly explain what it means. You have an entity here, such as a virtual machine. This could be also technically a physical server or a container that is running on top of a virtual machine. And you basically have two states. You have the original state, so before the recipe or the script is executed, and you have the state that is desired. For example, you have a plain Ubuntu machine, but the desired state, you want to have WordPress running on that machine. So what Chef is basically doing, it takes the recipe, which basically defines a bunch of actions, in order to transform the resource, for example, the virtual machine or the container that you're running on, from the original state to the desired state. If an error occurs at some point in time, what is done, and this is why it is called convergent provisioning automation, we are first of all in an inconsistent state. For example, only the database is running, but the application is not installed yet. So what is typically done, just the whole recipe is executed again and again until the desired state is reached. And this is why it is important to implement such a recipe in an idempotent manner. That means you as a developer of such a recipe have to ensure that all the actions basically are idempotent. That means it doesn't matter if you run this action once or twice or several times. Which is not easy, by the way.
They are requiring that this is idempotent.
Sure.
Okay, this is what they tell you. No, but they also guarantee that through their resources, there are some bugs, right? But with Chef resources, you are guaranteed to have idempotence. I can't use it.
There are some.
We tested that.
Yeah, sure. There are some default resources, for example, to install packages on software systems. But if you go more sophisticated, for example, if you wire your application to a database and you create a new table or whatever, and you run this task for a second time, it's hard to implement. You have to keep the state, for example, somewhere that you did this already in the past.
So this is like I recommend to write idempotent scripts.
Yeah, sure.
Okay. They don't enforce it.
They don't enforce it, but it's strongly recommended.
Yeah, sure.
Right.
Another question: is it possible to go back from the desired state to the original one? Because I had several problems.
Yeah, but not with this approach, but in the other talk or after lunch, basically, I will introduce Docker, and there you can have a very fine-grained snapshot approach.
Hard, right?
Yeah, here you would need another recipe that basically does the other way around, but this doesn't make sense, right? Or what you also could do, you just have a snapshot on the level of virtual machine. But this is not how Chef is working, right?
Can I just go back to the previous question and clarify these things? Because Chef allows you to use their own resources, which will enable you, for example, to download files and whatever. And through these resources, they do enforce idempotence, unless it's debugging implementation, right?
Sure.
But if you write your own shell scripts, which are part of the resource, there you have to do it on your own. And
True.
so just to make this so Chef does part of the enforce this.
And even if you implement your own resource type, so to speak, you also have to ensure idempotency. Because you cannot assume that someone is not using it in an idempotent manner. So, of course, there are more details. For example, you could use Chef solo without a Chef server, and yet you can, of course, ensure that the Chef script is only running once, right? But this is not the architectural idea behind Chef, right? So technically, a Chef recipe looks like this. So you define a bunch of resources. In it, for example, you say you need a certain directory which has a certain permissions and so on. You use this package resource to install a MySQL package on this machine and so on. And based on the run list, so each node, for example, a VM in your application, has a run list associated. And the run list basically tells which scripts have to be executed on which machine. And the run list, of course, refers to the recipes that have been implemented before. So you can say, on this node, I want to install Apache and MySQL. And then the Chef server takes care that these two recipes are executed accordingly. On the other hand, you have attributes. These are basically input parameters. And you could also use this for output parameters. That you say, for example, you define for this node, you define the attribute MySQL version 5.5, and then you can use it in your resource definitions in order to install a certain version of MySQL on this node. Then there is another mechanism which is called databags. Databags are basically databags is a mechanism that implements a key value store, and this can be used, for example, to synchronize data across nodes. So you could, for instance, in another script, deploy the database endpoint, then store it in a data bag. That means you store the IP address here, and then in another script you just read the data bag item. So there are methods implemented already by this domain-specific language. You read this data bag item from the database, and then you can use the IP address, for example, to put put the IP address in the configuration file of your application. So, and in terms of the community, as I said before, the community is quite active. So you find a lot of cookbooks and recipes to deploy middleware components and application components that are often used. So, like for example, popular databases, web servers, monitoring tools, stuff like that. And all in all, there are currently around 1,500 cookbooks available publicly as open source, and so you can just download them and use them in your applications. Who is using Chef? So there are a lot of companies that are actually using Chef in production, like Yahoo, Facebook is a big example. You also find on the Chef website, you find a nice video where some guy of Facebook is explaining how they are using it in order to manage thousands of machines, right? It's amazing to look at. So the next topic would be Docker, and I just have a look at the clock. Frank, when should we just talk? Maybe around 10 to 15 minutes. Yeah. Okay. So then Docker will be basically the last thing I present before lunch break, and the last part around CloudFormation and stuff like that I will present after lunch. So Docker in a nutshell, as I said before, it implements virtualization on the level of operating system. So compared to the hardware virtualization, where you always have a complete guest operating system with all the application and middleware components packaged in a virtual machine, you only have isolated processes. So this is what also Cloud Foundry and Bloomix is implementing in the background, right? And a host could be, for example, a virtual machine, a physical machine, and it basically runs the Docker daemon, which is basically a service that can be used using a RESTful API. And the Docker containers offers you isolation in terms of processes, file system, and networking. That means you don't have a full isolation like you have in virtual machines. You don't have a full dedicated operating system, but you share the operating system with other containers that may also run on the same operating system. A Docker file is basically an imperative build plan for containers. So you could also go, just say, I want to have a new container, a single command is enough, and then you do something in the container, and then at some point in time you snapshot it and say, okay, that's my state, this is the application component I need. But what you could also do, you can write a Docker file, which is basically a script, very similar to a shell script, and run or list all the commands you need to execute in order to build this container. So this is much more reproducible. For example, if the underlying operating system gets updated and so on, you can just rerun the Docker file as a build plan for the container to refresh basically the whole container. And it also gives you the ability of very fine-grained container snapshots. So at any point in time, you can execute new commands in the container, and then you can say, at this point in time, I want to create a new snapshot. This is especially nice if you're experimenting, for example. That means if you start, for example, deploying a certain middleware component, let's say a database server, and then you just play around with some modules, but you're not yet sure which are the right ones, so you can always step back to the snapshots, and this is very fast compared to virtual machine snapshots. This is usually less than a second, going back to a previous snapshot. So here it's also visualized the difference between virtual machines and containers. So for virtual machines, as I said before, you have a hypervisor running on the host operating system, and in each virtual machine you have a separate guest operating system. Of course, this gives you more flexibility, because here you could also run, for example, on a Linux system, you can use a Windows system here, and then you have all the binaries and libraries, middleware components to run your application component. But for each virtual machine, you have a separate guest operating instance. Container virtualization follows another approach. You basically have the Docker engine here, or any other engine that implements the container virtualization approach, so you don't have a complete hypervisor. And in the containers, you only have the binaries and libraries you need to run your application and middleware components. So the overhead is lower, but also the isolation mechanisms are on a different level, right? Because you share the operating system. So I introduced the approach of convergent deployment automation, provisioning automation before, that is implemented, for example, by Chef, and now we have a look at snapshot-based provisioning automation. So the setting is very similar. You have an original state that you want to transform a resource, for example, in this case it's a Docker container, into a desired state. How does it work? So you basically run the build instructions to reach the desired state, and this could be, for example, codified in a Docker file. So the Docker file defines all the action that you need to execute in order to transform the certain container from a plain Ubuntu container, for example, to a container that runs WordPress. If there's something wrong, the mechanism is a bit different. So you end up, as before, in an inconsistent state, but then you just reverse the work, basically, that has been done since the last successfully taken snapshot. So you just revert the work, and then you run this action again and continue with the other actions. So it's different to the idempotent approach, because in this case, you don't have to deal with implementing, or you don't have to ensure that all the actions are idempotent, because you just go back to the last step and then you continue. And using the snapshot-based approach, you can basically be sure that the other commands have not been executed yet, right? So it's a different model of provisioning automation. Here, this is a very simple example for a Docker file, which is basically the build plan for a container. It just lists a set of commands. For example, you clone a certain Git repository to retrieve your application component. Then you add some files that are stored in the context of this Docker file. For example, in this case, we assume that the WordPress configuration PHP file is in the same directory as the Docker file, so we can add it to the container in this directory. So we just copy this file into the container, and then we might, for example, do some permission adaptations and continue with our work. And in the end, we expose some port. For example, we need to ensure that the application we deployed is actually reachable from the outside world. So we need to explicitly define that our application is listening on port 80 to get an HTTP connection, for example. And then we run the application. For example, the run is a separate shell script that is implemented. So how can containers be linked? Because it's nice to have these containers, but it's because Docker basically allows you to deploy application and middleware components on a very fine-grained level. You need some mechanism to link these containers together, right? So you could have, for example, a Docker container that hosts the MySQL database that exposes this port, and you could have another container that basically has the WordPress application itself, but it somehow has to connect to the database because it requires it. Therefore, you can define so-called link aliases. For example, you can say, okay, this link has the alias db, and then you can, inside the container, access the credentials using environment variables that follow a certain schema. You just take the link alias that you need that you defined before, _port, and then you just access the port that is exposed by this container. And then you can read the context information, for example, to access the MySQL database. Of course, when you start with Docker, it's very simple. It's nice to get started, to run some containers, to build some containers, but if your application goes more sophisticated, you need some cluster management implementations in order to orchestrate a lot of different containers that you implemented. And there are already a bunch of solutions out there. For example, CoreOS is a separate operating system. I think it's based on Chrome OS, as far as I know. and they strip down all the parts that are not needed. So for example, it's a Linux distribution that doesn't have a package manager, because they say, it's too loud. Okay. They basically say that you deploy each and every piece of software using Docker. So you build Docker images for all the software components you need to deploy on your virtual or physical servers. You don't have a separate package manager. You all do it in containers. There is another solution by Google. You can integrate in the meantime Docker with OpenStack, for example, then you can use all the OpenStack tooling to orchestrate Docker containers, for instance. The community is pretty large already. I think Docker started around 1 year ago, and the community has grown a lot. So at the moment there are around 14,000 Dockerized apps that means you can download these Docker files, pre-packaged containers, in order to deploy your application middleware components. For example, Node.js, different database implementations that are used in many application stacks today. And there are already some companies that are using Docker like eBay or Spotify. Alright, I would say at this point in time we will have the lunch break, and after lunch I will tell you how to combine actually Chef and Docker. So there are some mechanisms that you can use, and also about CloudFormation, which is the orchestration language of Amazon. Thank you very much for your attention.
We are all back at 3 o'clock latest. But before we go to lunch, we all go and get a room picture outside.